My name is Kevin Hand, and I am a scientist at NASA's Jet Propulsion Laboratory in Pasadena, California. And my research focuses on the physics and chemistry, and potentially someday the biology of ice covered ocean worlds of the outer solar system. These are moons of the large planets in the outer solar system, moons like Europa and Enceladus and Titan. These are alien oceans that contain liquid water, and if we've learned anything from life on Earth, it's that where you find the liquid water, you generally find life. And so, with that much water in these distant oceans, the big question, the motivating question, the exciting question for me and my colleagues is if there's that much liquid water out there in these alien oceans, could there actually be life?
And that's also the subject of your kind of new book, which is kind of really how our paths crossed. Your new book is called Alien Oceans, and it's really about that, isn't it? It's about the kind of robotic probes that are kind of currently and will be exploring the kind of subsurface oceans and other places in the solar system where life could potentially be found.
Yeah, so my book, Alien Oceans, goes through a few different aspects of the search for life, both on Earth and beyond Earth. And I go through a bit of the history of how we've explored our own ocean and the depths of our own ocean, and what that exploration has taught us about the extremes of life on Earth, and how that information is helping guide us as we assess the habitability of these distant oceans. I go through a bit of how we think we know that these oceans exist, what kind of data have come back from spacecraft and telescopes that have enabled these kinds of insights. And then I also take sort of a forward-looking approach in the later chapters, considering what the future of exploring these distant worlds could bring. And in some of the later chapters, it's also fun because I speculate a bit about what life within these oceans might look like. For the most part, when we talk about the search for life beyond Earth, we're focused on even the tiniest of microbe. But there is some chance, at least I think there is some chance, that larger organisms could exist, at least within the ocean of Europa, where there might be oxygen dissolved in the water, and that oxygen could be potentially used by larger organisms. So I get a bit speculative later in the chapter or later in the book, and that's hopefully fun and interesting for the reader.
That's actually really interesting. I think for all the kind of talk about the search for life in the solar system, I've never actually heard. Personally, I've never actually heard anyone say that it could be anything more than microbial life. I mean, do you kind of foresee it could be something like fish, like kind of like aquatic life, like we see on Earth?
Well, who knows? So here's the comparison that I make. First and foremost, we don't really have a good understanding for how multicellular life came about on planet Earth. We've got a lot of kind of pieces of the puzzle, and those pieces are the following. First, multicellular life came about roughly 600 or so million years ago, and we often associate the Cambrian explosion with the rise of complex life. And the most important environmental variable that changed at that time, and that possibly enabled the rise of complex life and animals, was the rise of oxygen in our atmosphere. And so, obviously, we human beings know that we require oxygen. We breathe in oxygen and combine it with carbohydrates to fuel our life. And so, if oxygen is the key kind of energetic motivator for enabling multicellular life, then when we think about these alien oceans, we can say, well, is there any chance that these oceans have oxygen dissolved in the water and could power multicellular life? To the first order, the answer would seem to be no. And that's because on Earth, the oxygen, the abundance of oxygen that we have in our atmosphere comes from, of course, photosynthesis. And photosynthesis is driven by energy from the sun. And on worlds like Europa and Enceladus, the ice sheets are going to make photosynthesis a very unlikely niche for life. In other words, these oceans are trapped beneath ice shells, and these oceans are likely dark. The sunlight doesn't penetrate. Now, that depends on how thick exactly the ice is, and there's some outstanding questions there. So, at first, it might seem like photosynthesis and thus oxygen in the ocean is a non-starter. But then, at least for the case of Europa, there's a curious added process that's occurring, and that is radiolysis or radiation processing of the surface ice of Europa. Europa exists within Jupiter's incredibly strong magnetic field, and that magnetic field has got energetic electrons and ions, protons, all sorts of charged particles bouncing up and down along those magnetic field lines. And as that magnetic field sweeps by Europa, those charged particles bombard Europa's surface ice. And in the process, they split apart the water, H2O, into OH plus O and whatever else is there. It all kind of gets bombarded and broken apart and then recombined. And we observe on the surface of Europa, both with ground-based telescopes and with spacecraft like the Galileo spacecraft, we observe hydrogen peroxide and oxygen, so H2O2 and O2, in the surface ice of Europa. So radiation produces oxygen in the ice, and if that ice is mixed into the ocean below, you might have a way of oxygenating the ocean beneath the ice. Could that lead to the evolution of complex life? I have no idea. But there is a chance that the oxygen abundance is sufficient to support things like polychaete worms and other organisms that exist within our ocean on relatively limited oxygen supply. So it's an exciting prospect, and as I mentioned, it's highly speculative, but great food for the imagination and a lot of fun to kind of play around with.
I guess it's something that you're going to be investigating in the not too distant future, because you're involved in the new NASA mission to explore Jupiter's moon, Europa, which I assume will be a bit like the kind of Cassini mission at Saturn.
That's right. So the next step for Europa, there's actually two steps. One is the NASA mission, the Europa Clipper mission, and this mission will orbit Jupiter and fly by Europa some 45 plus times. Somewhat simultaneously, the European Space Agency will have a mission called the Jupiter Icy Moons Explorer that will initially orbit Jupiter, and it will fly by Europa twice, and then it will go into orbit around Ganymede. And so in roughly the late 2020s time frame, we could have two spacecraft investigating Europa and Ganymede and making a couple of flybys of the other large moons and just returning spectacular data from remote sensing. Now, neither of those missions has a lander on board, so those missions won't get us to the surface. But that's a mission that I'm working with a great team at JPL and across the country to hopefully move forward with getting a lander down to the surface of Europa. Right now, NASA has no plan or commitment to such a mission, but there are plenty of us in the scientific community and in the broader public who are tremendously excited about that prospect, because it's really only with a lander that can scoop up material off of the surface that you can then really look in fine detail for biosignatures, for signs of life, for the complex organics or the structures that you might see with a microscope. So that's a mission that I'm tremendously excited about. And then after that would hopefully come a mission that drills or melts through the ice and actually reaches the ocean below. And so my hope is that in the decades to come, we can pursue that really exciting program of exploring these alien oceans.
Wouldn't it be great if we could launch a sample return mission to actually bring, if one of the earlier missions were to find evidence for microbial life or something bigger, to actually be able to go and get it and bring it back to Earth?
So yes and no. So I'll dissect a couple of different aspects of that. So first, time and gravity are a real pain in the neck when you think about doing sample return. In the case of Europa, sample return would mean going down, getting a sample, dealing with all the complexity of getting that sample, and then launching a spacecraft that can get off of Europa and escape from Jupiter to get back to Earth. Now that's not impossible, but Jupiter's gravity well is a strong, deep gravity well that basically holds on to anything that comes into its realm. In the Saturnian system, we've got Enceladus, and we've actually looked at some sample return capabilities for Enceladus, and the concept there is that the plumes on Enceladus alleviate you from the burden of having to go down to the surface, having to land. And so you could fly by Enceladus numerous times, collecting sample from those plumes, and then swing back around to Earth, and that is feasible. It's somewhat enabled by solar electric propulsion, which can kind of slowly give you the accelerations you need. It would take a long time, and the amount of sample that you collect would still be quite small, because even though the images of the plumes of Enceladus look like these thick veils, they're really actually quite diffuse. And so you might only be getting a tiny tip of a pinky or thimble full of sample. And so that's a bit of a scientifically risky proposition. Coupled with that, as much as I would love to do a sample return mission and bring a microbe or other creature from a distant world back to Earth for detailed study, think about the planetary protection concerns. For any mission, we have tremendous criteria and regulations and cleanliness metrics that we have to meet to first make sure that we don't forward contaminate that world. In other words, that we don't bring any Earth microbial hitchhikers to, say, the ocean of Europa or the ocean of Enceladus. Second, to make sure that we don't contaminate our measurements. Heaven forbid we search for life on an alien ocean and we get a false positive by detecting a microbe that we brought with us. And that's just in the forward direction. Now imagine you're thinking about a sample return mission from one of those worlds, ignoring for the moment the technological complexity. Bringing a sample back then puts up this huge barrier of making sure that you contain that sample and protect our home planet from this organism. So, in theory, it would be wonderful. In practice, the technology and the planetary protection aspects put up huge barriers.
Do you think that if we were to complete a really thorough reconnaissance of the solar system and its moons in terms of the search for life, would you be more surprised that we did find life or that we didn't find life? Like, how likely do you think it is and that it's out there within our solar system?
Yeah, it's a great question, and one that I ponder quite a bit. And on the one hand, well, what this really comes back to is the fundamental question of, is the origin of life easy or hard? If the origin of life is easy and occurs in or under numerous conditions and doesn't require incredibly specific conditions, then I think the origin of life may have occurred many times on planet Earth and many times in our own planetary backyard, many times throughout our solar system. And so if the origin of life is easy, then I think we should expect to find life throughout our solar system. If the origin of life is exceedingly hard and life on Earth is some sort of biological singularity that requires conditions that we can't quite grok yet, then of course we might not find life anywhere in our solar system or beyond. But that's part of the importance of doing these experiments, these great experiments where we can actually go to Mars, Europa, Enceladus, Titan, Triton, you name it, and look for signs of life. And if we find it, then that's amazing, and we can begin to study life. And as I mentioned in my book, start to think about a great tree of life, start to think about a periodic table for life. How do we understand life in a larger context in a biological universe? If we don't find life, even though that's potentially less exciting, it is equally profound because it means that life is perhaps quite rare, not just in our solar system, but perhaps beyond our solar system. And it really turns the microscope back on our own tree of life. How did life on Earth begin? And to that end, I'll just briefly outline a bit of a debate in the origin of life community. There are many different debates, many different aspects about the origin of life that we're currently trying to understand. But one of the kind of main bifurcations is, does the origin of life require warm tide pools on the shores of an ancient ocean where sunlight can bathe that tide pool, and then the water evaporates and dries out the components and concentrates things like amino acids so they come together? Is that what the origin of life requires? Or can the origin of life occur in, say, deep sea hydrothermal vents at the bottom of the ocean? And it may be that the answer is both, or there are many different modalities. But if life can only arise, if life can only originate in rocky tide pools with just the right chemistry, then it may be that the Earth and Mars are the only place where life exists or has existed in our solar system. On worlds like Europa and Enceladus and Titan, there are no continents, there are no rocky environments. Everything is covered in ice and water. And so that modality for the origin of life would not work. But the deep sea hydrothermal vent modality could work on those worlds. So too, potentially a cold, icy origins, maybe something within the ice shell itself could help with the origin of life. But but this is a testable hypothesis. We can go to Mars, we can go to Europa, we can go to Enceladus, we can go to Titan, and see if life is there, and that will inform us about the modalities for the origin of life.
Yeah, because I suppose if it somehow turned out that life only arises on kind of warm, rocky Earth-like planets, then the search for signs of life has to go towards exoplanets, which is a completely different kettle of fish, isn't it? It's just so much harder, obviously, to look for life or signs of life on an exoplanet than it is to look for it on a planet within the solar system.
Yes and no, right? Because on the one hand, you're absolutely right in that we would be limited to the spectroscopy of the atmospheres, looking for chemical disequilibria, oxygen in the atmosphere coexisting with methane, and hey, we found life because these little squiggles tell us that in the spectra tell us that that only life and biology can cause this kind of disequilibria in the atmosphere. And that's exciting. Make no mistake about it. But it's hardly a close-up picture of an organism or a Europan squid. The flip side of that is exoplanets, as we continue to discover them and map out our stellar neighborhood and our galaxy, they also potentially give us a blueprint for where to target our SETI searches, where to do follow-up observations in the radio and the optical to potentially look for transmissions, which, that would be the ultimate biosignature and would be incredibly exciting. So yes, on the one hand, exoplanets could be limiting in the kind of life detection that we might have, because we're certainly not going to travel to them with robotic spacecraft anytime soon. But the other side is that maybe there is a signal that's propagating to us right now, and we just do not have our radio telescopes or optical SETI searches focused on those worlds.
Is that search for extraterrestrial intelligence, the kind of the sentient, intelligent life out there, is that something that you're actually concerned with in terms of your own research and your own kind of work?
Oh, absolutely. That's in part how I got my start. Captivated by ET and Close Encounters, and I worked for the SETI Institute many years ago, not directly on extraterrestrial intelligence, but on the search for life in the universe. But the work of my colleagues Jill Tarter and Frank Drake and others I find tremendously exciting, and we need to do more of it. I think there could be a signal out there, and we just have not completed a sufficient search across a wide enough band of the spectrum and across a wide enough slew of the night sky.
Okay. Well, yeah, it really is a fascinating subject, and I guess you've got kind of quite a lot ahead of you in terms of studying whatever data comes back from the Jovian system, and kind of trying to piece that together.
Yeah, at least in the next few decades. So you can think of it this way: the emergence and the evolution of life has a number of bottlenecks. One of which is the origin of life itself. Another of which is the origin of complex life, and then the origin of intelligence. Now, there are many different bottlenecks within that range, but at least within our solar system, we have the potential to see whether or not the origin of life bottleneck is truly a bottleneck. And if we find that life exists in numerous places within our solar system, then we can also explore that second major bottleneck is the origin of complex life, really difficult. And there again, we come back to potentially the ocean of Europa, where enough oxygen, in theory, could help um, motivate the evolution towards multicellular life. And then that last one, intelligence, who knows? And in my book, I speculate a bit about what intelligent life within an ice-covered ocean might look like. And here again, this is fun speculation. But think about it. Think about how much our ability as human beings, as Australopithecus, Homo erectus, Homo habilis, Homo sapiens, etc., how much our ability to look up at the night sky, to look up at the sun, to look up at the stars. Think about how much that ability to see the cosmos has motivated our desire to explore and discover. If there were to be life within an ocean like Europa's, maybe it's on some distant solar system. Imagine if intelligent life arose, some highly capable Europan octopi or what have you. It would not be able to see the night sky above. It would not know that it exists in space. It probably would not even, it would not have eyes in the way that we traditionally think of eyes. What would lie above would be an ice shell that's creaking and cracking from the tidal energy dissipation. And so it would have an extremely limited understanding, potentially, of its place in the cosmos. How does that then manifest itself in the evolution of intelligence? How does wonder and curiosity come about in an intelligent organism that doesn't even necessarily know to ask the question, are we alone? We look up at the stars and think about the planets, and it's obvious to us that this is a question to ask. Are we alone? But if you evolved in an ice-covered ocean, a dark ice-covered ocean, what is the existential crisis that kind of alien octopi undergoes as it ponders its existence? So again, a lot of fun speculating about these things, but these are some of the questions I like to ponder.
Definitely, it's definitely food for thought. I think we'll leave it there on that kind of existential question, Kevin. But yeah, thanks very much for speaking to me today, and it's just been absolutely fascinating. Thanks again.
My pleasure. Fun chatting with you, and thanks for taking an interest in my book, Alien Oceans.